Okay, thanks for joining us for the Western Wheels Conference. A couple quick things before we begin. If you need a certificate, you'll find the link for that here. You'll need to submit a separate request for each session that you attend, and you should receive your certificate in email within 24 hours of submitting the request. If there are any handouts available, you'll find those there. And if you're interested in learning more about any of the products featured in our sessions, that'll take you to the product page for each one. And if you click request pricing, that'll add it to your wish list. Here we are at the wish list. You can either complete the form and submit it right away, or you can keep browsing around and adding items to it to get one big quote. And you can always get back to your wish list right up here in the top right-hand corner. That's it. I hope you enjoy the session, and we'll see you on the other side.
Hi, my name is Cardell. I'm with DYVO, and I want to thank you for joining this training session. This class is intended for both automotive instructors and technicians. For instructors, I think it's safe to say that electricity is one of the hardest subjects for students to understand. And even for advanced, experienced technicians, electrical problems are not something that they typically enjoy in their shop. In this training session, we're going to take a look at a new way to diagnose electrical problems. The objectives for this session are to learn how we can diagnose easier, quickly, accurately, and with confidence. If we can better prepare our students for tackling electrical problems, we can ensure their success in their careers as the electrical systems on vehicles increase in complexity. Today I'm here with Joe, who's in the automotive program at Arapahoe Community College. Joe, how long have you been here in the automotive program?
This is going to be my second week this week.
Your second week, okay, so brand new to the program?
Yes, sir.
All right, and what do you know about electrical circuits on cars?
I do not know anything about electrical circuits on cars.
Don't know anything, right? And that's to be expected. You've only been here for 2 weeks, so we can't expect you to know that much about it.
Of course.
Right. Okay, well, Joe, what do you notice about this car right here? If you take a look at the front of it here, what do you notice?
Well, I noticed that the headlights are on.
Okay. Yeah, we've got one on, and what do you see about the other?
Well, it looks like one of them appears to be out.
One of them is out, absolutely. So that's actually the first step in diagnosing, is verifying the customer concern. So you've already got that part down. What we're going to do here is I'm going to give you a couple of bits of information, and we're going to see if you can diagnose this headlight.
Okay.
All right. So the first piece of information I'm going to give you is that for this light bulb to work, it needs a positive and a negative. All right, so there's two things it needs, positive and negative. Okay, without those two, the light bulb isn't going to work. All right, so what are the two things it needs to work?
A positive and a negative.
Positive and negative, awesome, okay. The second piece of information I'm going to give you is that green is good, red is bad. All right, really complicated, I know. Green is good, red is bad.
Green is good and red is bad.
Exactly, yep, perfect. So what's the two signals that it needs to work?
Positive and negative.
Awesome.
Green is good, red is bad.
I think you're ready to diagnose this.
Perfect.
All right, so since Joe's never done this before, I'm going to walk him through a few of the steps, but ultimately he's going to be the one who comes up with the diagnosis. So Joe, we're going to be using DYVO to diagnose this. So what I want you to do is, right now, I've already got the battery clamps connected to the battery. Okay, so that's connected, and this is the other side of those battery clamps.
Okay.
All right, so go ahead and take DYVO there.
All right.
And take these clamps. Okay, now I want you to take a look here at both sides of DYVO here. We've got two ports on both sides. What do you see that it says on that side?
This side says circuit.
Okay, and what about the other side?
And the other side says battery.
It says battery, all right. We're connecting to the battery, so where do you think you want to plug these two wires into?
Into the battery side.
Perfect, so let's go ahead and do that.
All right, so we got positive to positive, and we got negative to negative while
awesome.
We're using DYVO.
If you look over here, notice that you do have your battery voltage, but you also get this LED, and what did I tell you about green?
A green would be good, so from looking at this, I would say that the battery would be good.
Awesome, all right, perfect. So now let's go ahead and let's test our circuits and see what's going on with this headlight, okay?
Okay, perfect.
So if you noticed on the other side, that's where it said circuit.
Yes, sir.
So go ahead and take your test leads right here that we've got.
Okay.
And let's plug those into the circuit side there.
All right, and then positive to positive, negative to negative.
Yep. And Joe, have you ever used this before?
I've actually never used this before, no.
Okay, all right, cool. And is any of this staged? Have we rehearsed any of this? Have we ever done this before?
We have actually not, no.
Okay, all right. Just want to make sure that that's real.
Yes.
All right, cool. Then we're going to go in here and take a look at the headlight. All right, just to help Joe out, I've already pulled the headlight bulb out, and I've got the forward probes into the connector, and this is just going to make it a little easier for him to get into that. All right, so Joe, why don't you go ahead and take your circuit test leads right here and plug those into your forward probes.
All right, perfect. So again, black to black and red to red.
Okay, so Joe, have you ever diagnosed any circuits before like this? Have you ever gone through anything like this?
I have not, no.
You've never gone through anything like this? Okay, so what were the two signals I said that you needed?
Green is good, red is bad.
Yep.
And that one appears to be red. So if I had to guess, I would believe that this would be the faulty circuit.
Yep, exactly. And when you look at these right here, you see our positive right there.
Yes.
And we get our green LED, so you're telling me the positive is good?
Yes.
And the negative right there, you get a red, so you're saying the negative is bad?
Yes.
Yep, so just like that, Joe diagnosed a ground issue, a negative side issue, just based on colors, only being in the program for about 2 weeks.
Yes.
Yep, awesome. Thanks a lot, Joe. I appreciate it.
Of course, man. Thank you for having me.
You're welcome. All right, we're going to get back to diagnosing with DYVO in just a second, but first I want to take a look at some of the other tools that we may use to diagnose this headlight. So as we see, the driver's headlight is working and the passenger headlight is inoperative. So let's first start by using a test light and seeing how we could diagnose this headlight. All right, with the bulb removed and I can clearly see that it's not working, I'm going to unplug the bulb and I'm going to forward probe the connector. This way I can test the pins without damaging them by using the proper forward probes. All right, now to use the test light, I'm simply going to loop it between my two forward probes. So I'm going to plug one end into one forward probe and the other end to the other, and I'm looking for the test light to light up. You can see that it does illuminate. What that tells me is that I have my positive and negative circuits to the headlight connector. So based on the test light, that means that the headlight bulb is defective, the headlight bulb is open, and so I should replace the headlight bulb because I have positive and negative according to the test light. Next, I'm going to use a multimeter and I'm going to check voltage. So we're going to move that to the voltage setting, plug my test leads into the voltage section for those, the two voltage ports, and then plug these into my positive and negative circuits. And that tells me I have 12.15 volts at the headlight connector. Now, this isn't actually a valid test. And the reason for that is because we don't have a load in the circuit. So some of you may have caught that. A lot of you may not have. A lot of people use the multimeter just like this. They'll plug it in place of a component and they'll get a voltage reading. So according to this, we've got 12.15 volts. This looks good. We want to see 12.15 volts, but this is not a valid test because we don't have a load in the circuit. So to use the multimeter on volts, it is going to require me to put the headlight bulb back in and back probe the connector. We want to be careful that our back probe pins don't touch each other and also that we don't damage the weather insulation or the wires when we do this. All right, I've got my back probe pins in, so next I need to connect my test leads to the back probe pins. All right, so we've got 12.14 volts at the headlight connector. We have the bulb plugged in. So this test coincides with what our test light was telling us, which is that our positive and negative circuits to the headlight bulb are good. Again, we need to replace the light bulb. So what I'm going to do is I'm going to remove this light bulb. All right, here is a brand new light bulb. And it still doesn't work. So what happened? What went wrong? Both the test light and the multimeter told us that we had our positive and negative circuits to the headlight bulb, that we should replace the bulb. I did that and it still doesn't work. So something went wrong here. Now, one of the other tests we could have done was using a multimeter and putting it on ohms and checking the resistance or the continuity of the circuit. Now, I'm not a big fan of that, and there's a lot of reasons why. One of the issues with resistance tests is that we can really only test the ground side of the circuit, it's going to be very uncommon to see in service information for them to tell you to do a resistance test across the positive side of the circuit, going from battery positive all the way to the positive of the component you want to test. And the reason for that is because the multimeter in ohms puts out its own voltage and current. And to be able to accurately detect that, you can't have voltage and current in the circuit. You can't have system voltage and current because it will affect the readings of the multimeter in ohms. So what this means is that you have to disconnect the circuit and you have to eliminate the voltage and current in that circuit. When you do that, there's a lot of things on the positive side of the circuit that will not work. Things such as relays, switches, control modules, all things that will send out that power or send out that voltage. You're not going to be able to test that all the way back to battery positive because those circuits have to be off. So to test the resistance on the positive side of the circuit, you actually have to break up that circuit into different sections, which is a lot of extra work to do just to get that resistance reading. This leaves us with only testing resistance on the ground side. And this is one of the reasons why I don't like resistance test readings, because you're only able to test 50% of the circuit. When you're testing circuits to a component, we need to test all of the circuits. In this case, for the headlight, the positive and negative. The resistance test is only going to get us the negative side, 50%. We're still not going to be able to test the positive side. So it doesn't give us that much information. Some of the other reasons for not doing resistance tests is that because to do the resistance tests and remove the voltage and current in the circuit, the best way to do that, especially when we're working with parallel circuits, is to disconnect the negative cable on the battery. Remember that if you do that, you are losing all of the volatile memory systems of that vehicle. So we're talking about diagnostic trouble codes, freeze frame data, emission monitors, and then we're also talking about all of the comfort features that the driver or the customer of the vehicle is used to. So things like radio presets, memory seat positions, and now that we have the infotainment systems, we can also lose things like Bluetooth pairing. This can be very frustrating for a customer to get their vehicle back and to get in it and have it feel like a completely different vehicle where everything that they knew about it has been changed or lost. So removing the negative battery cable just to do a resistance test is not ideal. In addition to that, let's remember that the multimeter in ohms puts out 1 milliamp and typically less than 1 volt. That's not enough to accurately load circuits down and get a good reading. A resistance test will tell you with just one strand of wire that you have perfect continuity. But we all know that if we have one strand of wire to something like a headlight, we're going to get severe voltage loss, and that headlight is not going to be very bright or maybe not even on at all. For these reasons, we should really minimize the amount of resistance tests we're doing when it comes to testing circuits on cars. All right, we saw where both the test light and the multimeter told us that the positive and negative circuits to the bulb are good and that we needed to replace the light bulb. We replaced the light bulb and we still have the same issue. So what happened, what went wrong, and why did these lead us down that direction? This is one of the problems that so many technicians are having when they're diagnosing circuits on cars. We obviously know that the circuits are becoming more and more complex. The amount of electrical systems we have on cars is overwhelming. And especially when we have new students that are starting out and they're trying to figure out how to do some of these basic, simple tests, they're using some of these test equipment and they're not sure if they should be going between volts and ohms and which setting they should be going in and what ports to be plugging in and where they should be connecting to. Let's not even get into the whole idea of voltage drops. And if you do a voltage drop from positive to positive or negative to negative or the negative to positive or positive to negative or across the headlight bulb, there's so many different combinations with that. It's very confusing for students and even experienced techs that have been doing this for decades. So we need to find a better way to test and diagnose circuits so we can be fast, efficient, accurate, and have the confidence in our diagnosis and knowing that that's the right thing to do, that that's the right thing to fix, or that we're not just putting parts in cars. So let's take a look at using DYVO and how we would go about diagnosing this headlight. All right, my first step is to take the DYVO 22-foot leads and connect them directly to the vehicle's battery. On the left side of DYVO it says battery, and this is the side I'm going to plug the other end of my 22-foot leads to, red to red and black to black. As soon as you make that battery connection, you can see that DYVO powers on, it goes through a self-test phase, and then you're ready to begin testing. So on the right side it says circuit, and we have our red and black ports, and this is where we're going to connect our test leads to test any circuits we want to test. So red to red, black to black. On the left side of DYVO is our battery information. One of the great features with DYVO is that you can constantly see your system voltage while doing tests. So as your battery voltage fluctuates, you can see that live reading. The green LED tells us that the system voltage is within range. We can see we're at 13.44 volts and the word OK appears. If the battery voltage drops below 12 volts, the red LED comes on and it indicates low. If you put the battery on a charger and it starts charging above 15 volts, the LED changes again from green to red and the word high is displayed, and that tells us that the battery voltage is too high. Now on the right side of the screen, we can see that we have 2 LEDs and 2 numeric values. The top value in LED is for your positive circuit, so that's any positive circuits you want to test, and the bottom right value in LED are for the negative or ground circuits that you're testing. Now for our positive and negative circuits, we have 3 LED colors. Green means a low voltage drop, yellow means a medium amount of voltage drop, and red means a high voltage drop. Now DYVO is a true dual channel meter, meaning that the positive and negative circuits are independent of each other. With a traditional multimeter, you have to connect both test leads. The multimeter then displays the difference between the 2 test leads. With DYVO, our test leads are independent of each other, meaning that you don't have to use both test leads. If you want to just test one circuit at a time, you have that ability. Now the reason that both of our circuit LEDs are red right now is because we're not connected to anything, so it's telling us that we have a really high voltage drop on both of our circuits. We also see on the screen that it says V loss. That means that we're in the voltage loss mode. This is telling us how much we're losing on each circuit. The last thing we see displayed on the screen is the word load. DYVO is currently in load mode. This is the most powerful feature of DYVO. In load mode, DYVO acts as a known good component and can load circuits down, forcing current to flow through them to give you the most accurate results. We want to use load mode anytime that we want to load circuits down and force current to flow through them. So things like headlights, tail lights, power windows, door locks, fuel injectors, any of these actuators, motors, or systems that perform work, that's when we want to use load mode. We do not want to use load mode on sensitive computer circuits, signals from sensors, and communication lines, as well as airbags. These are all systems we do not want to use load mode for. We'll talk more about load mode later in the video. All right, now let's get into testing this headlight bulb. Now, with traditional multimeters, as I showed, when you want to test this light bulb, the only option is to leave it plugged in and to back probe it. But because DYVO acts as a known good component when we're in the load mode and will load circuits down, this gives us the ability to now unplug components and a forward probe, which makes it much easier to test circuits. Right now, I need to be able to know which circuit is positive and negative. If I had a wiring diagram, then I could look at that and see, but since I don't, I'm just going to take a guess. If I'm wrong, I'm simply going to swap my test leads. So I'm going to start with my circuit negative first. And you can see as soon as I plug in the circuit negative, the LED changed from red to green. That green is letting us know that we have a low voltage drop on our ground circuit. So all the way from battery negative to this headlight connector, we have a low voltage drop. We can also see the numeric value tells us that we're not losing any voltage across our ground side. So already I know with 100% confidence the ground of this headlight bulb is good. Now here's a perfect example of how our circuits are independent of each other. I don't have the positive circuit connected to anything still. I only have the ground, and I'm able to take a measurement on the ground circuit. So this is how we can just use one at a time if we want. But the benefit of DYVO of being able to test 2 circuits at the same time, I'm going to take advantage of that and now plug in my positive circuit. We can see that the positive circuit does not change at all. The LED remains red, which alerts us that we have a high voltage drop on the positive side of the circuit. And we can see that we're losing 13.40 volts from our battery positive post all the way to the headlight connector. Now, a lot of people like to see the voltage available rather than the voltage loss. If we were using a traditional multimeter, this would require us to move our test leads to different sides of the battery in order to get that reading. With DYVO, we can press the mode button. And when we do that, we see it change to the voltage available. So we see on our positive circuit, we don't have any voltage available to our headlight connector. A quick explanation of the voltage available versus voltage loss. We can see here that we have 13.39 volts at the battery. We have 13.39 volts lost across the positive circuit. 13.39 minus 13.39 means we have 0 volts available. Changing between voltage available and voltage loss is just simply personal preference. It makes no difference on testing whatsoever. All right, so when we look at DYVO at a glance, we can clearly see why this light bulb is not working. It's not working because we don't have a positive circuit to this headlight bulb. That red LED is a big indicator that we have a problem on the positive side of the circuit, and that's why this headlight bulb doesn't work. This is the huge advantage of DYVO, is that it's able to find problems that other methods miss, such as the test light and the multimeter. All right, let's take a look at the problem that I put in this vehicle that caused both the test light and the multimeter to not be able to pick up. In the fuse box here, and it is a resistor. So in place of the fuse, I took that out and I have a resistor in place. Now this resistance is low enough that allows enough current to flow for the test light to still illuminate. Same thing with the multimeter in volts, is that it'll still pick up a full battery voltage, but as we saw, DYVO is able to detect resistance issues from low resistance all the way up to high resistance issues very easily. Let's actually check the bulb itself. To test the headlight bulb, I'm going to disconnect my circuits here. We no longer need to test the circuits for our headlight because we already know that the circuits are good. I'm going to take the positive test lead and I'm going to connect it to a known good ground. Okay, so I'm just going to clamp it on to a known good ground. Now I can verify that that's a good ground by taking the other end of my test lead and plugging it into the circuit negative or ground for DYVO. We see that we get a green LED and a low voltage drop of 0.00 volts. That tells me that's a good ground. So we verified that that ground is good. I'm going to plug the black test lead back into ground. On our light bulb, I'm going to use the DYVO forward probes and I'm going to forward probe the terminals of the light bulb. The other end of my red test lead that's connected to ground, I'm going to plug it into one of the forward probes. It does not matter which forward probe I connect to. Either one will work. So I've connected to one side of that. Then my black test lead that's connected to circuit negative, I'm going to connect to the other forward probe. Here we're looking at the circuit negative value. We have 0.04 volts. Just like your traditional multimeter, the lower the value, the lower the resistance. The higher the value, the higher the resistance. Because this is a light bulb that uses a lot of current and has a high wattage, we're going to have a low resistance for it because it has a lot of current that goes through it. 0.04 volts is a very common value for headlights. If DYVO said 0.00 or even 0.01, that would indicate that the light bulb is shorted and has no resistance. If DYVO displayed 13.2 volts, that would indicate that the light bulb is open. The big difference between DYVO and a multimeter when testing components is that DYVO is able to apply a full battery voltage and also load that component down to give you much more accurate results than what you're going to get from a multimeter in ohms. Here I have a defective light bulb, and let's look at the difference between this one and our known good. Again, it doesn't matter which terminal I connect to the headlight bulb. Now notice our circuit negative value stays high at 13.22 volts. This tells us that we have an open in that headlight bulb because the value is really high. Just like your traditional multimeter, the higher the value, the higher the resistance. 13.22 volts is almost exactly battery voltage. This means that this headlight bulb is open. All right, next we're going to take a look at how to use DYVO in the high impedance mode. So we're just showing using DYVO to load circuits down for headlights and fuel pumps and power window motors, things like that. But what about when we want to test sensitive circuits such as throttle position sensors? We don't want to alter those signals, we don't want to affect them, so we need to take DYVO out of load mode. We need to turn the load mode off and turn it into a traditional high impedance multimeter. So you can see right here I've got my throttle position sensor. There are two sensors inside here, as all of our electronic throttle control systems have. And I've got my back probes into each of those signals. And so looking at DYVO, the first thing I need to do is to take it out of load mode. So I'm going to press and hold the mode button down for about 3 seconds. You see load is turned off from the screen, and we're now in our high impedance multimeter mode. Now we're still in voltage loss, and I want to use this as a 2-channel meter, so I'm going to press the mode button one more time, and that's going to get me into the voltage available mode. And now we can see we're at 0 volts for both our positive and negative circuit, and this is going to work like a 2-channel multimeter. Now, the LEDs are based on the voltage in the circuits. For our circuit positive, we want to see all of our battery voltage on circuit positive. Because we're at 0 volts, our LED for circuit positive still remains red. Now for circuit negative, the LED is green because we don't have any voltage on our ground and we don't want voltage on our ground. So depending upon what you're testing with sensors and signals, especially a lot of 5-volt circuits, the LED colors may not be applicable because we're not looking at our traditional system voltage for this. So now I'm going to take my test leads and plug one into one probe and one into the other. Now it doesn't matter which probes I connect because they're both a dual channel, so it doesn't matter which one I connect where. Now I'm going to move the throttle plate and we can see those voltages change. And that's wide open throttle right there all the way up to almost 4.5 volts. And as I slowly let that out, we see it steps back down. With DYVO, because we have this dual channel mode, we're able to see 2 different signals at the exact same time. We wouldn't have been able to do this with a traditional multimeter. We would have had to either take 2 different readings, which wouldn't be compared at the same time, or we would have to have 2 different meters hooked up together. Having this dual channel mode opens it up to test so many different things at the same time. You can test both accelerator pedal sensors. You can test a mass airflow and an engine coolant temperature sensor and see how they relate to each other as the engine warms up. You can test both CAN high and low circuits at the exact same time. Now we're going to take a look at Console Labs Wiper System Trainer and using DYVO to diagnose it. We've got the battery right here. This does require an external battery. I do have it connected to a power supply to help maintain the battery. These are the 2 test leads off the Wiper System Trainer. So I'm going to connect those to the battery. Then we're going to connect DYVO. So we're going to take the 22-foot leads. I'm going to connect one side to my battery negative and the other side to the battery positive. The other side of my 22-foot leads are going to be plugged into the left side of DYVO where it says battery, red to red, black to black. Then we're going to connect our test leads to the right side of DYVO where it says circuit. Again, black to black, and then red to red. And the fault we now have is that the washer pump does not spray. We still see the wiper motor works, and it works in, of course, all the other functions as well. But when I pull it back, I don't get the washer pump spraying. So first thing we can see is with DYVO, we see our battery voltage is at 13.55 volts. And the reason, of course, that that's higher is because the battery is on a charger. We get our green LED and the battery says OK. So off the bat, we already know that our system voltage is good. The first place I'm going to test is at the washer pump. Now, because the washer pump isn't working, I don't know if it's a wiring issue or if it's the pump itself. Looking at the wiring diagram, we see the washer pump or washer motor, pin 1 is our voltage and pin 2 is our ground. So I'm going to take the positive lead, the voltage lead for DYVO, and I'm going to put that in pin 1. And then my negative test lead, I'm going to put that in pin 2. Now immediately I see that for my ground I get a green LED and I see 0 volts on my ground side. So I know that my ground is good. What we don't have is our voltage side because we have a red LED. So that positive LED is red. That tells me there's an issue, and we can see we have 13.52 volts that are being lost in the positive side of the circuit. Remember, that's not voltage available. To see voltage available, a quick press of the mode button cycles to our voltage available. So if you prefer that mode, we can see here that we have no voltage available at the washer motor. Now, of course, that's because the switch is not activated. So I'm going to pull the switch back, and we can see that we don't have any change on the positive side of the circuit. I still have my ground, but my positive is bad. So just like that, we've diagnosed the reason that this washer motor is not working is because it is missing voltage. Looking back at the wiring diagram, we can see from the multifunction switch that voltage is supposed to come out from pin 7. So I'm going to move my test lead here to pin 7 of the multifunction switch. We don't need the ground anymore. We've already verified that that's good, so there's no reason to even continue testing that. Pulling back on the multifunction switch, and we can see we get a green LED and it tells us 13.3 volts. And just like that, our diagnosing is over. We've already identified the problem. We have an open circuit or high resistance between our multifunction switch, pin 7, and the washer motor, pin 1. There's nothing else that we need to do in this case. Now, a lot of people in this case may be inclined to take a multimeter and put it in resistance and test resistance between pin 7 and pin 1. There's no need to do that. There's no need to take those extra steps. We've identified that there is an issue in that circuit. And truthfully, it doesn't matter if it's an open or if it's high resistance, because the repair is going to be the same either way. We know we have a problem in that circuit. The next steps, of course, after getting customer approval is going to be to go through that wiring harness and identify exactly where the problem is and then repair that issue. You can see that DYVO makes diagnosing really simple. A lot of people, when they're using their multimeter, are constantly switching between volts and ohms. They're never quite sure which one to go with. Using DYVO, there is no switching back and forth. There's no reason to do those extra steps. You can easily and very quickly identify the problem and then move on. Now, if we wanted to test the washer motor itself and see if the motor is open or shorted, because we could have two issues. We could have a problem that we've already found in the wiring harness, but we could also have an additional problem with the washer pump motor. It's going to be really simple. We're going to simply unplug the motor. I'm going to use the DYVO forward probes that come with the Pro Kit, and we are going to use those to access the pins to the washer pump motor. I'm going to take the positive test lead. I'm going to connect that to my battery ground, and I'm going to connect the other end of that test lead to one of my forward probes. It does not matter which one I connect to, either one will work. And then I'm going to take my negative test lead here and plug it into the other forward probe. We are in the load mode for DYVO, and we can see that it says 0.24 volts. That indicates that the washer pump motor has some resistance in it. What we don't want to see here is a straight 0.00 or even a 0.01, because that would indicate almost no resistance. That would be a short inside the motor. And we also don't want to see a very high value. A really high value, such as the full battery voltage of 13.52 volts, that would tell us that the motor is open. Now, if you find it absolutely necessary that you want that resistance reading, you can always go to a computer, or you can simply grab your phone. You can go to DYVO.us. You can click on the resistance calculator, and you simply input the values. So our battery value is 13.52 volts. And the VLOS value is 0.22 volts, and that calculates out at 1.24 ohms. I've got the fault reset, and I've got a new fault put in, and that new fault we can see is that the high speed doesn't work. So low speed works, our intermittent function works correctly, our mist function, and the washer pump now works again with the wiper motor. So what we're missing here is high speed. The first place I'm going to go to is the wiper motor, and we can see that pin 2, the orange wire, is a hot and on signal. So I'm going to use my positive test lead. I'm going to go to pin 2. I am in the load mode for DYVO, and we are in the voltage available. If I wanted to see how much I'm losing, I can quickly press the mode button, and I can see that I have no loss on the positive side of my circuit. So we know that pin 2 is good. Let's test pin 5. That is our ground. Again, we're in load mode, so we know that we're loading and stressing that circuit down. We get a green LED for ground, so I already know that pin 2, my positive, and pin 5, my ground, are good. Looking at the wiring diagram, pin 4 is the positive to the high speed. So I'm going to move my test lead over to pin 4, and we get a red LED. With the test lead at pin 4, our multifunction switch is in the high setting. We should be getting a green LED for our positive circuit, and we should have a very low number, a low voltage loss. So we're able to very quickly identify that the reason that this motor is not working in the high speed is because it's missing its positive signal. So we're going to look at the wiring diagram and look to see where that comes from, and that comes from pin 2 of the multifunction switch. So I'm going to move this down here to pin 2 and test there, and we can see that we don't have any output from the multifunction switch. Now I'm going to verify that the positive and negative circuits to the multifunction switch are good. The wiring diagram shows that pin 3 to the multifunction switch is the positive in, so I'm going to go to that. That is good. Remember, we're looking at our voltage loss, so we have very little loss on the positive side. If you want to see voltage available, we're at 13.47. And of course, we need to test pin 1, which is the ground to the multifunction switch. So we know that the multifunction switch has the positive and negative that it needs to operate, and it is not sending out the positive circuit at pin 2 to the wiper motor. We just diagnosed the multifunction switch is defective. Now, to give you an idea of what that should look like, I'm going to take the fault out, and let's move this to pin 2, which was our output. We can see with that yellow LED that we do have some voltage loss on the circuit. In this case, it's nothing to be concerned about. That yellow LED is just alerting you that you do have some voltage loss on the circuit. We have 13.14 volts available. I hate subtracting, so I'm just going to use the V loss mode, and I can easily see that I have a 0.2 volt loss on that, which is perfectly acceptable. There's nothing wrong with that 0.2 volt drop. We're going to go back up to pin 4, which was at the motor itself. And we can see that we have a 0.23, 0.24 volt loss, so just a little bit more, but everything is working. Next, we're going to look at the Consult Labs electric power steering trainer. So we've got the battery right here. I've got it connected to a power supply. That's just going to maintain the battery. We've got obviously the electric power steering system here, the whole module, and then DYVO with the accessories we need to test this system. So the first thing I'm going to do is I'm going to start by taking the trainer module. It has its power and ground here for the module, and we're going to connect that to the battery. Then I'm going to connect the DYVO test leads to the battery. The other side of my test leads are going to plug directly into the left side of DYVO where it says battery, black to black, red to red. DYVO power is on. Then we're going to take our circuit test leads and connect those to the right side where it says circuit, red to red, black to black. So right now there are no faults in this module. There is a fault box up here, but all of them are off, so everything should be functioning fine. We do see that with DYVO it's telling us our battery is 13.53 volts. We get that green LED and it says okay, so we know everything is good there. Of course, we get that higher voltage simply because it's on the battery charger. We look at the power steering motor. On this side here, the way that this module works is that we turn it, and when I do this, you're going to feel an assist, and you're also going to see the amps move one way or the other depending upon which way I turn this. So when I turn it clockwise from this position, you can see that we get kind of a negative amperage, and when I turn it counterclockwise, we get a positive amperage reading, and that's the electric power assist that we're getting. Now what's cool about this is that you can have somebody hold on to one side, which is going to simulate resistance from the road, from the tires, and then on this side you can spin it. And you can tell just because of that electric power steering assist, there's no way to physically hold this. This side will always be able to overturn the other side. And that's kind of how you can, students can see how that electric power steering system is working. So let's look at how students would go through this using DYVO testing a known good system. Now, of course, one of the first basic tests that we can do is we can test the big 60 amp fuse right here. And I'm just going to use the positive side of DYVO, testing the positive circuit. We are in the voltage loss mode. That's why it's reading so high right now. So remember, this is telling us how far away we are from our battery voltage or how much we're losing. So I test on one side of the fuse. We see the LED goes green. It says 0 volts. I'm going to test on the other side, and we also get green. So we know we have a good fuse. Looking at the wiring diagram, we can see the electric power steering control unit. Pins 4, 5, 6, and 7 are all for the torque sensor. And there's actually 2 torque sensors inside. And they're using that for a redundancy purpose. So we're going to have a voltage reference and our ground, and then our 2 signal circuits. Now, because we're testing signal circuits, we don't want to affect those circuits. We're going to take DYVO out of load mode. So I'm going to push and hold the mode button down for about 3 seconds. We see the word load disappears. And now I also want to change it from voltage loss to voltage available, and that's because I can really use this as a 2-channel multimeter. So we're first going to start with pin 5, the brown wire, which is labeled as TSV, and that is the torque sensor voltage. That is the reference circuit that goes to the torque sensors. So I'm going to use my positive here, and I'm going to test at pin 5. Now we can see we have 8.22 volts. Yes, the LED is remaining red because 8.22 is not a good voltage source if we're on that 13.53 volts. So you need to remember that when you're checking sensors and low voltage circuits, that the LEDs are not necessarily going to apply. So here we see 8.22 volts. That is because Nissan is running an 8-volt reference circuit. It's pretty rare. I know most of the times we're used to a 5-volt reference, but for this torque sensor, they're using an 8-volt reference. So we see 8.22 volts there, so I know my reference circuit is good. The next circuit we're going to test is pin 7, and that's TSE, and that's for the torque sensor earth, or the ground circuit. So I'm going to use my negative test lead here, and I'm going to go to pin 7. And we can see that we have 0 volts across there. Now in this case, the green LED is applicable because we are testing a ground circuit and we want that to be really low. Now this is sometimes, of course, because we're in a high impedance mode that meters can throw you off, and you can see 0 volts and think that you actually have a ground when you don't. We have 2 different options here. In most cases, it is okay to use DYVO to load down a low reference circuit. So I'm going to do that by pushing and holding the mode button for about 3 seconds until load appears. And now we can see, and you saw how it went also from 0 volts to 0.02, because there is a little bit of loss in there, but perfectly acceptable. This is how we can verify that that ground is good. Now there are some vehicles where loading the low reference circuit to a sensor is not a good idea. There are some control modules where that may be a little too much for it. But in most cases, you can load down that low reference circuit just like we did here. If you're not sure if you can load it down, or if you just simply don't want to because you're worried that, that it may have some other impact on it, another thing that we can do is I'm going to hold my test lead steady right here, and I'm going to wiggle the negative wire. And you notice how the voltage for my ground is staying very steady at 0 volts. It's not jumping around, it's not moving. That tells me that I have a good ground connection, or a good connection to the pin that I'm testing. Watch when I take this out. Can I rest it there? Notice that it's still really low, it's 0.02. But when I wiggle this around, notice how the numbers fluctuate and my LED colors are also jumping around. And that's because I'm not connected to anything. This is actually picking up all of the electromagnetic waves that are in the air, as well as the energy from my body. That's causing this value to jump around like that. So we know if we don't want to put it in load mode and we want to test our good ground circuit, I can hold this in place and I can wiggle this around, and the numbers aren't fluctuating, the LED isn't fluctuating. That's how I know I've also got a good connection to my circuit there. So we now have verified the reference voltage and the ground coming out of the control module that goes to the torque sensor. The next thing we want to do is test both torque sensor outputs. So pin 4 and pin 6 are the torque sensor signals. So I'm going to put this test lead on pin 6 and this test lead on pin 4. Now it doesn't matter in this case because we're using this as a dual channel multimeter, right? So we could put it this way, we could actually flip it around and do it this way. It doesn't matter because we're on that same scale where they're both at 0 volts. So it really doesn't matter either way, we're checking that. And this is one of the really cool things that we can now see. Before, when you had a multimeter, you can only check one circuit at a time. So to do this, you would have needed 2 multimeters. With DYVO, we can actually see both torque sensors at the exact same time. We see one sitting at 2.49 volts and the other at 2.52. I'm going to now turn the shaft here, and we can see going down in one direction is causing that voltage to drop, and it's going from 2.5 down to 2.3, 2.2. I think I even saw 2.1 right there, and I can even hold this right here and really try to, and we can see it all the way down to 2 volts right there when I try to hold that back from turning. Now let's go ahead and turn it the other way, and we can see we get a positive increase on both circuits. And again, the same thing, I can hold this here and I can turn this, and we can see how much we can get, almost to about 3 volts on both of those. So we know that both torque sensors are working. They are outputting the correct voltage. It goes positive in one direction and it goes negative in the other. We've also verified the voltage reference and the ground to the torque sensors. You see how quickly we went through that, just how fast it is to be able to check a torque sensor. Now let's move on and test pin 10. That is an ignition signal. So we're going to test that with the positive test lead, and I'm going to put that here to pin 10. Now we can see it says 13.53 volts and we get a green LED. Now remember that the load mode is off, and because this is an ignition circuit, we can see this comes up from a fuse. We definitely want to load this circuit down. We want to verify that this is a good circuit. So I'm going to press and hold the mode button. We see that load now comes on the screen. We're loading it down. I feel confident that the ignition circuit that's providing power all the way from fuse 2 to the control unit is good. That circuit is good. The wire integrity is good. If I wanted to see the voltage loss, a quick press of the mode button shows me that I am not losing any voltage across that positive circuit. Now our last two wires that we can test on this connector is pin 9, which is our CAN high, and pin 16, which is CAN low. Now just like the torque sensors, we want to take this out of load mode because we don't want to affect the CAN circuits. So I'm going to push and hold the mode button, take that out of load mode, and now we're ready to test those. So I'm going to place this on pin 9 for our CAN high, and my negative test lead on pin 16 for my CAN low. Now because this system is isolated, meaning that we're only looking at the electric power steering control unit, there's no other control modules in here, that does change our CAN values. So I know that these are a little bit off from what we would normally see on a functioning car with all the systems on it for our voltage values for CAN, but for this trainer module, these values are normal because we only have one module on this system. Now I'm going to introduce a fault into this. And if you notice when that happened, the motor actually just spun that shaft on its own. I didn't touch that. So let's go ahead and see what's going on. I'm going to go to turn this. I don't have any assist, and I see that my amp gauge isn't changing at all. So now if I held on this side, I can easily, I can hold on to that and prevent this from turning. So let's go ahead and start with codes. Now this is a working DLC down here. So I'm going to connect a scan tool. I'm going to scroll down to the electric power steering, and I'm going to look at codes. So we have torque sensor malfunctioning, an electric power steering motor malfunction, and then we also have an undocumented code. So now of course we can put those codes into service information and follow the diagnostic flowchart. To keep this simple, I'm simply just going to test the torque sensors and now see what they're outputting. We've got load mode off for DYVO. I'm going to start with pin 5, which was my reference voltage, and we can see we still have 8.4 volts there, so we're good. Then I'm going to test pin 7, which was my low reference or ground, and I'm going to load that down to make sure that that's good. And it is. Now I'm going to test the sensors themselves. And look at the difference in those voltage values. Before we were sitting around 2.5 volts for both of them, and now we see one at 5.58 and one at 4.86. So clearly we're on the right track here with the issue, and as I turn this, we don't see any change in those torque sensors. I know that if my torque sensors have the correct voltage reference and ground, they should be operating correctly. We can see that they're not, so we could determine this as being defective torque sensors. Now, if this was a real vehicle, we would probably do some additional testing on it where we're actually getting into the harness and disconnecting it at various places and testing those sensors. For this training module, the only places that we really can test are at this breakout connector here that they have for us. Based on this information, we would condemn the torque sensors. I've got the faults removed from this, and the last thing I want to show you is how to test for current flow. Now, this, of course, being an electric power steering motor, is going to require a lot of current. We can see obviously by the amp scale that goes up to 30 amps, and knowing that the fuse is rated at 60 amps, this is not something we would want to take a typical multimeter and put in series to test for current, because we're most likely going to blow the fuse inside the meter. So this is where we're going to want to use an amp clamp, and DYVO works really great for that. So let's see how we're going to do that. I've got an adapter right here. I'm going to unplug my ground. We're going to plug this in place. So that just simply gives me another output here. I'm going to take DYVO out of load mode, and I'm also going to put it into my voltage available. Now I've got an external amp clamp here, and this uses a BNC connector typically used for scopes. So we just are going to use an adapter that goes BNC to our 4mm banana plugs. If your amp clamp already has banana plugs to it, then you wouldn't need this piece. I'm going to plug this into the ground side. So there's two sides of this. One is ground and one is signal out. I've got my little ground lead there, so that comes out. And now the next thing is going to be our signal wire. Test lead, plug it into the signal wire, and now I can plug it into either one of my circuit ports. It doesn't matter which one. I'm just going to plug it into my negative circuit. I'm going to turn the amp clamp on. If you notice here that our scaling in the 20 amp mode is 100 millivolts equals an amp. Now we may have to bump this up to the 60 amp scale, I'm not sure yet, but we need to keep in mind that every 100 millivolts is equal to 1 amp. I'm going to zero the clamp out. I usually do that a few times, and now I'm going to clamp around the easiest place to get to, which I'm thinking is just going to be right up here. We're going to go around, I can go around either side of the motor here. And now when I spin this, we can see that that voltage jumps up, and depending upon how much I can really spin this, I saw 0.22, there was 0.28. I'm going to try to hold this side here and turn it and see if I can really, there we go, 0.7. So if we know that every 100 millivolts equals an amp, that's 700 millivolts, so that's roughly 7 amps that we see that this motor is using. So you want your students to learn how to test current flow, how to use amp clamps. This is a really great way to do it. They get to play with it and they can see, they go onto this side and then they can take this off and they can go over to the positive side, and how does that look different when they go one way versus the other, and how does that current flow change. So really great way to be able to see that using this training module with DYVO and that external amp clamp. Let's take a look at diagnosing one of the console lab engine stands here using DYVO. Now I'm going to use the fault box here, and it's really easy. There's a lot of different faults that are already programmed into this that you can go in and you can set up. So I've got a fault in here, and it's for the fuel tank pressure sensor. There is a DLC connector on this training module, so I've got the Tech 2 plugged into it. I've gone into my codes, and I can see that there is a P0452 fuel tank pressure sensor circuit low voltage. After seeing the trouble code for the fuel tank pressure circuit low, I went into our PID values here, and I'm looking at the fuel tank pressure sensor, and we see that it says 0.00 volts, and that corresponds to the code that we have for fuel tank pressure circuit low. I've got the battery on a charger. I'm now going to connect the DYVO 22-foot leads directly to the battery. On the left side of DYVO, it says battery. We've got a red and black port, and that's the side I'm going to connect the other end of my 22-foot leads to. Black to black, red to red. On the right side, it says circuit, and that's the side that I'm going to connect my circuit test leads to. Because I'm testing a sensor, I'm going to take DYVO out of load mode, so I'm going to push the mode button down for 3 seconds until load disappears. And then I'm going to press the mode button one more time, and that's going to cycle it to voltage available. I want to test the signal circuit, which is the middle green wire. I'm going to use my red test lead. I'm going to connect a back probe pin to that, and I'm going to back probe the circuit wire there. Now, DYVO is showing that at the sensor, the signal wire has 1.43 volts, but on our scan tool PIDs, we see that we have 0 volts for the fuel tank pressure sensor. This tells me that either we have a wiring problem between the sensor and the computer, or that the control module is defective or having some issue that's causing it to not read the correct voltage. Now, using the black circuit negative test lead, I'm going to test the pin at the control module. And here we have obviously this very nice breakout box. We're looking at pin 24 for the fuel tank pressure sensor. I'm going to put that right in there, and we can see that our circuit negative, which is on pin 24, is showing us that we have 0.02 volts. This matches what the scan tool is saying. So if the scan tool is saying 0 volts, and we can see that we're physically measuring 0 volts at the control module, then the control module is seeing the correct voltage. The problem is, at the sensor, we have 1.43 volts, and at the control module, we have 0.02 volts. So we can 100% identify that we have a wiring issue between the sensor and the control module. It's either an open or a high resistance. It honestly doesn't matter because the repair is going to be very similar. You're going to have to get into that harness, isolate where the issue is, and repair it. Now, there's a lot of people at this point that would want to grab a multimeter, put it in ohms, and test resistance between the control module and the sensor. There's no reason to do that. That's a complete waste of time. We have already identified that there is a wiring issue between the sensor and the control module. There's no reason to take additional steps to test resistance. And the resistance test isn't going to be as accurate. Remember that a resistance test will show you 0.00 ohms with just one strand of wire holding it together. So it will show a good connection when indeed we don't have a good connection. Here we've easily identified that there is a wiring issue between the sensor and the control module. No additional steps needed to take. If you're going to do the resistance test, you'd have to disconnect the negative battery terminal, you need to unplug the sensor, you have to unplug the control module, and then you've got to go between those two. There's no sense in doing all that extra work. We've already identified that there is a wiring issue between these two. Now, when you're doing sensor diagnosing, there's actually something really cool that you can do with DYVO, and that is that you can use DYVO to drive the signal up or down, depending upon the type of circuit it is. So if you have a sensor that when you unplug it, normally the signal sits high, then you can use DYVO to drive that circuit low. If you have a circuit that normally sits low, you can use DYVO to drive that signal high, and you can watch to see if the scan tool PID changes to know the wiring integrity, as well as if the control module is able to register those differences. So let me show you how to do that. All right, the first step is to unplug the sensor that you want to drive the signal. So we're going to do the fuel tank pressure sensor, and I'm going to unplug that connector. Then I'm going to use one of the DYVO back probes that comes in the kit, and I'm going to put that into the middle wire because that is the signal wire. The scan tool value is showing us that the fuel tank pressure sensor is at 0 volts. Now remember, that's with the sensor unplugged. This means that the signal normally sits low at 0 volts and requires the sensor to pull it up high. We're going to use DYVO to pull that signal high. So because it normally sits low, we're going to use the circuit negative, and I'm going to use a test lead and plug that into my circuit negative, and then I'm going to plug the other end into my forward probe. To pull the circuit high with DYVO, I'm going to put it in load mode. You see with DYVO that the value went up to the 13.32 volts because that's the maximum that it can pull it up to with this battery voltage. But if you look at the scan tool PID, it says 5 volts because that's the maximum that the computer can read on this 5 volt circuit. Now, it does not hurt the control module that we are applying the 13.3 volts to this circuit. There are internal resistors inside that control module, and it is protecting it. Now, by being able to use DYVO to pull the circuit up at the sensor, we see that change on the control module. That tells me that the wire integrity is good. We don't have an open, we don't have a short, we don't have any resistance issues, and that the control module is also functioning correctly. It is responding to the voltage that we have applied to the circuit. So by doing this one test, we've verified wire integrity and the control module functionality. Being able to use DYVO to pull circuits up or down is a really powerful feature, so I want to show a few more examples of this. I'm going to unplug the mass airflow sensor / intake air temperature sensor. I'm going to forward probe the intake air temp sensor signal. With the intake air temp sensor unplugged, we can see that the scan tool value is showing us -40 degrees, which is the coldest it'll read. It's the absolute extreme, and that's what happens when you unplug the intake air temp sensor. I'm going to connect my test lead from the intake air temp sensor into the circuit positive. Now we see that the voltage is 5.03 volts, and that's because with the sensor unplugged, 5 volt reading means -40 degrees for the intake air temp sensor. Now with DYVO, we can pull this circuit down and actually make it go all the way to 0 volts and force the temp sensor to read in the opposite extreme. So by turning the load on, we can see that on DYVO, the circuit positive value has gone down to 0.1 volts, and the intake air temp sensor has gone to its extreme of 269 degrees. With this one test, I just verified that the integrity of the wire between the sensor and the computer are good, as well as the control module being able to register the change. I'm going to test are the 5 volts and the low reference. I'm going to keep DYVO in load mode. In most cases, on most vehicles, this does not pose a problem. However, loading the 5 volt and the low reference on some circuits could overdrive the current for the module, and it could cause damage. So if you're not sure, then I would recommend taking it out of load mode when you're testing the 5 volts and ground. On this vehicle, it is perfectly fine to load the 5 volt and the low reference. It applies a very light load, so it won't damage the module on this. So I'm going to keep DYVO in load mode, and that's going to give me the most accurate values. So I can see that I have a 5 volt and it is loaded down. It's a full 5 volt, so I know it's good. I'm going to take it out because I don't want to put it in there for too long when you're loading down 5 volt and low reference. Now I'm going to use my black test lead here for my negative, and I'm going to back probe the low reference, and I see that I get a green LED and it tells me 0.07 volts. So again, I don't want to do that for too long. Just put it in there, make sure that you've got good circuits. So right now I know with the sensor, my 5 volt reference is indeed good, and the low reference or ground circuit is also good to the sensor. Now let's use DYVO to see how we can test a fuel injector circuit. Here I've got the fuel injector back probed. I'm going to turn off load mode. And I'm also going to go into voltage available mode. Now with the fuel injector, we see both our circuit positive and negative at 12.74 volts. That's because we have key on, engine off. We've got 12 volts going to one side of the fuel injector. The other side is not grounded, so we're seeing that same 12.7 volts on the other side. Here we see that the circuit positive stays high at 13.7 volts and we have a green LED. Our circuit negative is mostly high with the occasional pulses, and that's showing us that the control module, the ECM, is controlling the fuel injector. It's pulsing it on and off, and we're getting those yellow flashes. So what we saw with that was that the circuit positive LED stayed green, and we had that 13.7 volts. That showed us that our circuit positive to the fuel injector was good. Now on circuit negative, we saw it mostly red with occasional yellow flashes. The reason for this is because our fuel injectors are mostly off with brief pulses of being on. When you get those brief pulses of being on, that negative circuit gets pulled down low to close to 0 volts. Now what DYVO was showing is that when it was mostly off, we had the red LED for circuit negative, and when it gets pulsed on, we saw a yellow LED. Remember, a yellow LED means that you have a medium amount of voltage drop. That's very typical of a fuel injection circuit because we're always going to have a little bit of voltage loss on both sides of the circuit. And on the ground side, that comes from the control module, and that control module isn't able to pull the fuel injector all the way to a true 0 volts to get that green LED. It's able to pull it close to that, and that's why we see the yellow. So we saw that red, yellow flickering back and forth, mostly red, the brief pulses of yellow. That tells us that the control module is controlling the fuel injector and that the wire integrity between the control module and the fuel injector is good. All right, now let's say we want to go a little bit further with it and we want to test the fuel injector itself rather than just the signals to it. So I'm going to unplug our probes. I'm going to unplug the fuel injector. Use the DYVO forward probes to forward probe the injector. I'm going to take the red test lead, connect an alligator clamp to it, and connect that to a known good ground. Now, if I'm unsure if I've got a good ground, I can always plug it into my negative here to test for ground. I'm going to load that ground down, and I can see that I got a green LED and it says 0 volts, so I know that that's a good ground. So all I did with DYVO there was just verify that the ground I used was good. Now I'm going to take one of my forward probes, it doesn't matter which one, so I'm just going to pick that one, and I'm going to plug the red test lead, which is connected to ground, into that forward probe. My negative test lead, I'm going to put that into the negative side of DYVO. We're still in load mode, and I'm going to connect to the other forward probe, and I see a value of 1.86 volts. Now this is just like using a multimeter to test resistance of the fuel injector. The difference is that DYVO is able to more accurately load the fuel injector and therefore get better results than what your multimeter and ohms can. Just like the resistance test, if we see a low value such as 0 volts or 0.01, that would indicate that the fuel injector is shorted. If we see a really high value such as battery voltage of 13.4 volts, that would indicate that the fuel injector is open. A value in between that indicates that the fuel injector does have resistance. If you want to know the exact resistance, you can go to DYVO.us from a computer, or we can just simply pull up from our phone, go to resistance calculator. Here I'm going to put in our battery voltage of 13.46 and our circuit value of 1.88 volts, and it tells us the calculated resistance is 12.1 ohms. Thank you so much for attending this training session. I hope you got a lot out of it. With all of the advancements in technology on the engineering side of the automotive industry, our goal here was to help those on the repair side. The better equipped we are to quickly and accurately diagnose electrical problems, the more successful we'll be.
Okay, that's it. A big thanks to Cardell and the DYVO team for putting together that session. Be sure to check them out at our website, dactic.com/DYVO, or right through here at the partner section. You can request a Dactic discount on any of their products here. And there's also more information on what DYVO can do that your meter can't, as well as some testimonials and some how-to videos. So be sure to check those out, and we'll see you next time.